Hi everyone, my name is Ashdeep Singh. Today I'm going to present my work on passive similarity based CNN filter pruning for efficient acoustic scene classification. This work is done along with Professor Mark D. Plumley at CBSSP University of Surrey, UK under the project AI for Sound. Convolution neural networks (CNNs) have shown state-of-the-art performance in many applications. However, CNNs are resource hungry due to the large size and heavy computations. The heavy computation they rise from the multiply accumulative operations, which are predominantly in convolution layers. This makes a bottleneck to deploy CNNs on resource-constrained devices, where the power consumption, the memory requirement, and computation speed is an important issue. Moreover, training CNNs for more time it emits more CO2. As an example, a GPU running for 2 days it emits CO2 which is equivalent to driving an average car for 20 kilometers. Therefore, it is really an important task to reduce the computation complexity of CNN so that they can efficiently deploy it on hardware despite of their state-of-the-art performance in software level. In the literature, it has been shown that CNNs may have redundancy in their parameters. For example, the weights or the filters might be redundant. And the existing lottery ticket hypothesis says that it's always possible to find a subnetwork from the original network which achieves similar performance as that of the original network. Therefore, this work it aims to make CNNs efficient by removing or pruning the redundant parameters. The pruning of the network or the connections in CNNs can be done in two ways. One way is to prune individual weights from the network, which comes on the weight pruning. Now, removing individual weights from the network, it results into a prune network, which is an unstructured network. And other method is the filter pruning method, where the whole filter from the network is removed and the resulting network is a structured prune network. Now, if we see this unstructured networks, it requires extra hardware software for efficient acceleration despite removal of connections. On the other hand, filter pruning method, it doesn't require any extra specialized hardware or software for efficient acceleration due to structured prune network. Therefore, filter pruning methods are pretty popular. Now the question is how to measure the importance or to identify which filter to keep or which filter to prune. So to answer this, in literature there exist two broad class of methods. One is the active method, other is the passive methods. Active methods, they use the data set to identify the filter importance. On the other hand, passive method, they use the only the information of the filters without involving any data set. So passive methods are relatively simpler one. Okay, therefore we propose a passive filter pruning method. We hypothesize that the similar filters they produce similar outputs and hence mostly contribute to redundancy and can be eliminated. Okay, so we propose an algorithm where we identify the similar filter pairs, okay, closest pair to each filter, and then we remove one of the closest pair of the filter. This way our method can preserve the diversity learned in the CNN layers, and it removes the redundancy among filters. This is on contrary to the existing pruning methods, where the relationship among filter is not considered, and the existing method they define importance based on the norm of the filter, which is nothing but the weighted sum of the filter, and a high norm is considered as relatively more important than others. So we argue that a norm is not a good metric to measure the importance of the filter, because it ignores the mutual relationship among filters. And apart from that, under high pruning ratio, when large number of filters have to be pruned, under those situations, norm-based method always tend to select the high norm filter without worrying about how redundant those filter might be. Right. So we propose a similarity-based method, which gives the diverse set of filters, and it performs better under high pruning ratio, where the large number of parameters or filters are removed from the network. So we follow four-step methodology. We are given a pre-trained network, which in our case is the DKS 2021 task 1 baseline. It has 3 convolution layers, around 46 key parameters, and it requires 286 million multiply accumulated operations for inference, uh, corresponding to a 10-second audio length. So given this pre-trained network, we used the proposed algorithm 1 to identify the important filters in each of the convolution layer independently. Then we remove unimportant filters from the network from a subset of layers, and we obtain a prune network. Now given the prune network, perform a fine tuning for only 30 epochs to regain the performance loss. So what we achieve is that we propose a passive filter pruning framework that doesn't require any user-defined pruning ratio, which means that as compared to the norm-based pruning method, where you can rank the filter based on the importance. However, to need top few important filters, you need to use a user-defined pruning ratio. On the other hand, our method will automatically select which filter are important, which are not. Okay, and the proposed similarity based method, it outperforms the existing norm based pruning methods. And we analyze how many training examples are sufficient to regain the performance of the prune. Found that only 75% can be used to regain the performance of the prune network as compared to fine tuning with the all training examples. To measure the performance of the proposed pruning method, we computed the accuracy of the prune networks, which are obtained by pruning different convolution layers. Now, in the underlying pre-trained network, we have 3 convolution layers. So we prune different subset of convolution layers. So ultimately, we have total 6 prune networks, where C1 indicates that only the first convolution layer is pruned. Okay, and C1 plus C2 plus C3 indicates that all 3 convolution layer are pruned. Here, this red line, this indicates the baseline performance with 100% parameters and the accuracy without performing any pruning. And this blue objects, it shows the accuracy obtained when there's no fine tuning over the prune network is performed. Okay, so we find that there's a decrement of accuracy after pruning the network. Okay, and after performing the fine tuning, most of the accuracy is regained at fewer parameters. In comparison to the norm-based method, that is the norm-based pruning method, we find that the accuracy obtained using the proposed pruning method is better than, and as the number of parameters eliminated from the network increased, the drop in accuracy for the proposed pruning method is lesser than that of the norm-based pruning method. Okay, so this is where the advantage of the proposed pruning method is, where we are selecting the filters based on the similarity rather than based on the norm, which always tend to select filters based on the high norm. And under scenarios where we are pruning or removing more parameters, it is really important to consider the diversity in filter selection, which which is given by the proposed method. Now to show the filters which are selected in the proposed method, so we plotted the L1 norm of the filters versus the filter index, and we find that the filters which are selected in the proposed method, they they also have the smaller norm, and the proposed method also ignored the high norm filter as well, because it carries the similarity with other filter. This is where the advantage of the proposed method is, where we do not bother about the norm of the filter. We only care about the similarity and the redundancy. So based on the redundancy, we have selected the filters despite its norm. So next we analyze the accuracy versus training data percentage. We analyze that without performing any fine tuning, the accuracy obtained using the proposed pruning method is is around 5%, 5 to 6% better than that of the random initialization and the norm-based pruning method. And as the training data increased from 0 to 10%, there's a sharp regain in the performance, which is from maybe from 15% to around 40% when for the prone network where all layers are prone, and mostly the accuracy is regained by using only the 75% data during the fine-tuning process. So this is where one can save the computations during the fine-tuning process without using all data. Let's use the 75% of the training data um, and perform the fine-tuning. Okay, next we analyze the prone network accuracy with the different methods when the important filters are obtained using different distance matrices. The proposed method, it uses the cosine distance, base distance similarity. We also try with the Chebyshev distance based method and the average filters, where we 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 compute the similar filter pairs based on the cosine distance, and then instead of removing one of the similar filters, we average the similar filters and use the average filter as the important one. And we find that uh, these methods like average filter or norm-based method, the random initial method, they perform more or less equal to the random, is around 10% performance, and these are the method that do not work. So this is, we thought it's really informative to try the methods which are not working, so that in the future whenever somebody is trying to use a distance metric, so there's no need to waste the time on these methods because they didn't work well. So in conclusion, what we find that the proposed filter pruning framework, which is passive, doesn't use any data set, it reduces 25% of the parameters and 27% of the multiplier cumulative positions at a drop of less than 1% accuracy when the prune network is fine-tuned for 30 epochs only. We find that fine-tuning using few training examples improves the performance of the prone networks significantly, and only 75% of the training examples shows the similar performance as obtained using the all training examples. So we can reduce the computation complexity by reducing the number of training examples as well using the fine-tuning process. And the proposed pruning method, it outperforms the existing norm-based pruning method, which considers the norm of the filters to define the importance. Thank you very much. I would like to acknowledge EPSRC for any funds. If you have any questions, queries, discussions, please visit my post. Thank you very much.